of teaching one course.
Yes, and the worst part is having to listen to each other quietly.
Listening to each other is okay.
I think we can start. We already have 52 people.
Yeah.
So we'll be going live in a minute.
I can't hear you, Sabrish.
Is it okay now?
With a crackle, yes.
Yeah, too much crackle. Yeah.
Yes. I hope it's fine now.
That's much better.
Yeah, okay, sure. So it's just gonna turn screen. Yeah, so we are live. Good evening, everyone. So to welcome you all to the second installment of the Mimamsa Science Fest. Today's event is a panel discussion or conversation, you might call it, between Dr. Satyajit Rath and Professor K.B. Mohanan, who both of whom can be referred to as Satyajit and Mo respectively. The topic of today's discussion is two secular theories of biological evolution, Darwin's theory and the intelligent design theory, potential scientific theories or pseudosciences. So with that, I leave the floor open to the panelists.
Okay. Satyajit, so can I begin by saying about a few things that to set the ground, make sure that the terrain is reasonably well understood. I think there are three things that we need to have some kind of agreement on. One of them is what we mean by scientific theory, because the question that we are raising is, are these theories fully fledged scientific theories, or are they theory seeds? So I'm going to suggest that scientific theory must have the following requirements to be called a scientific theory. One of them is that a theory should correctly predict observational generalizations and explain those observational generalizations. And there's a slight difference between predicting and explaining, even though explaining requires predicting. The other is a scientific theory should not make incorrect predictions, because if it makes incorrect predictions, then we say there is a flaw in the theory. And it also means that we have to look for possible cases of incorrect predictions, look for possible counter evidence. There should be an active search. And the final requirement is that we must show that what we claim to be predictions are indeed derivable from the statements of the theory. So this is kind of like saying that proving that a mathematical theorem is indeed a theorem by proving it from the axioms and definitions. The same thing applies to scientific predictions. Otherwise, we may have the illusion of prediction, but not actual prediction. So that is one requirement of scientific theory. And I think I'm assuming that you and I agree on that. So Satyajit, is that okay? Are you?
So this is going to lead to a continuation of a conversation that Mo and I have been having for a while. And I'm going to put it out there, even though we came to a sort of quasi-amicable resolution of that, I'm still going to put it out there. I worry deeply that in the uncertain evidentiary terrain of the life sciences, where actual empirical evidence is fragmentary, is difficult to get, is deeply confounded by all sorts of issues. I am deeply uncomfortable speaking of scientific theories with that intangible reverential quotation mark that Mo puts around the phrase. I tend to talk about what I think is a more moderate, speaking of moderation, a property unfamiliar to Mo and me, but I tend to prefer to talk about a more moderate notion, the notion of an explanatory model. You have a framework of explanations in which a few things connect to each other, and you're using those to predict, as Mo says, and I'm in complete agreement, to predict or explain. I'm just very uncomfortable putting too much of a weight of demand on these contingent, provisional, explanatory models. And I worry that the phrase scientific theory begins, even when we don't quite intend it, begins to put that sort of a weight on the model. And in fact, I think that from the perception of somebody who's not an evolutionary biologist, for example, the notion of theory begins to take on such an air. So that's my agreement tempered with caveat.
Okay. So my strong feeling is that we don't really disagree. I agree that these are actually norms of theory, but it is extremely hard to fulfill those norms. So there may be a gap between the norms and the actual practice, but we try our best to obey those norms as much as possible, knowing fully well that perfection is impossible. The other is, we are not going to explain everything. There will always be, a huge bunch of facts that we are not able to explain. There will be counter evidence, but the whole enterprise is to do the best we can so that when we find two theories, we can say, okay, this one is better than the other theory. Without some norms, it will be difficult to say why one theory is better than another theory. So the norms are set up in order to say which one is better, which one is completely bad, semi-bad, and so on. So I think we may use different words, but I think we agree. And to really see whether we actually agree or not will take a few weeks of discussion, maybe a few years of discussion. But that much of agreement is okay for me. I just want to put out the norms, and you want to be skeptical about the total adherence to the norms. Yes, fine. Okay, so that broad terrain is fine. The other thing that I wanted to be reasonably clear about is, what do we mean by evolutionary theory? So that we can say there are 3-4 competing evolutionary theories, not just Darwin's theory, but there can be other evolutionary theories. And for that, you have to say, what is the crucial, the non-negotiable assumption of an evolutionary theory, such that if the two of us have two different competing evolutionary theories, we would agree on at least that particular version, what the core of evolutionary theory is. So I would say something like the, let me read it out. Theory of biological evolution is a theory whose central proposition, non-negotiable proposition, is that all existing and extinct species on the Earth evolved from a single unicellular ancestor species, or as Darwin said, a small number of ancestral species. So it doesn't have to be a single ancestor. It can be, as Darwin was clear in saying, small number. The important part is the number of species that we have now is much larger than the number of species that we had at the beginning. And we don't even have to use the word theories, because Darwin had difficulty in defining, we still have difficulty in defining species. We could just say taxa. So We will say Drosophila is a taxon, insect is a taxon, mammal is a taxon, vertebrate is a taxon. All these are taxons. So the question that we're talking about is the number of distinctions that have emerged since the beginning. So if that is not done, it is not an evolutionary theory. Okay, so we are both talking about evolutionary theories. We accept evolutionary theory in this sense, but we may have disagreements on the specific version of evolutionary theories. All right, so let me check with you again. Are we on the same planet on this?
So let me start with a reservation about competing theories. I tend to worry about looking at, to use your phraseology, competing theories in which one will be better than another, or one will be wrong, one will be right. I tend to think, again, based on empirical historical experience, that pretty much all of them have something to contribute to modifying our understanding and making a better theory, or making a better explanation.
Yeah.
So this isn't so much a traditional Upanishadic debate where the winner, who is always Yajnavalkya, gets to take all the cows home and nobody else gets anything. So that's the preliminary. As far as evolutionary theory is concerned, I think one prerequisite is that we all acknowledge that there has been evolution, which is really a different way of saying what you said, that a great diversity of life forms that in the short term are heritably stable have emerged over the long term from pre-existing by heritage, by inheritance, from a much smaller number of earlier life forms. That's sort of the broad outline that I'm rewording this as. So what then you are calling competing evolutionary theories, for me, simply become arguments about possible mechanisms by which this may have happened. And in that formulation, we then begin to debate which mechanisms are likely to be more prominent and more impactful than which other mechanisms. And in all of this, I'm really trying to make an argument that this is really an inclusive search for what seems to make sense, where there seem to be gaps that other perspectives from other intellectual domains sometimes tend to have something insightful to contribute in terms of mechanisms. But again, with those restatements and those caveats, yes, I agree.
Let me also add that here, even here, we don't really disagree. I think when I said competing theories, what I meant was something like this. Any theory is a collection of integrated propositions. There are many propositions in a theory. Sometimes when you look at two theories, you find that in some cases, you have a proposition in one theory that the other theory doesn't have, in which case there is no logical contradiction. The other theory can absorb it. So they're complementary. There is no logical contradiction. But occasionally we do find logical contradictions. And when we do find logical contradictions, the proponents of the two theories must engage in a debate. Debate does not mean win or lose. They both win, because after all, the idea is to contribute to our understanding. So what happens is, when you have a logically contradictory proposition, we look at this very carefully and restate that in such a way there is no contradiction. Occasionally, it might mean abandoning one of the two propositions. That doesn't matter. But in some cases, what happens is you discover that both propositions will have to be abandoned. So for example, if you take the strong position that light is a wave, not a particle, and light is a particle, not a wave, they're contradictory. But if you say that light has properties of both particles and waves, there is no contradiction, that disappears. And quite often, this is what happens in the history of science. So I think it is this aspect of including understandings of different kinds and putting them together that you are emphasizing. And I'm emphasizing the need to look for logical contradictions very carefully. And if you have logical contradictions, eliminate them. Right now, there is a logical contradiction between, for example, the theory of quantum mechanics on the one hand and relativity theory on the other. And people have been trying to, solve that logical contradiction for a long time. Sometimes people say they have been able to solve them, but that's the enterprise. If there is a contradiction, eliminate the contradiction and actively look for potential contradictions, because we may have them without even knowing that there is a contradiction. So I think we don't disagree. We just seem to have different, we're looking at it from slightly different angles, that's all. Okay, so if that's the case, we can go to the third one. And that has to do with the word intelligent design. Now, I agree that intelligent design is typically associated with a designer who is God. And this typically comes from the Judeo-Christian view of God as the creator versus God who set up everything in such a way that human beings would emerge in the course of evolution. So this is not possible in a scientific theory. You cannot have a supernatural entity like God. So that we all agree that that is not a possible scientific theory for reasons that I will not go into right now. The sense in which I'm using the word intelligent and design is in the sense in which, for example, people like Wolfram has a book on the intelligence of the universe. And there have been others, especially in computer science, who have been talking about the intelligence of the universe. Let me read out one particular statement of that idea of the intelligence of the universe from, let's see, Cursor. Okay, here is Ray Kurzweil says, again, the idea is intelligence of the universe. The universe, he says, the universe has been set up in an exquisitely specific way so that evolution could produce the people that are sitting here today, and we could use our intelligence to talk about the universe. Now, there is a strong version in this idea of intelligence. Universe has been set up, kind of suggests that somebody set it up. That's not what I have in mind. What I have in mind is that something like the initial conditions of the universe, whatever the causal factors were, the initial conditions were such that, and also the properties of the universe were such that evolution happened. So, for example, the properties were such that atoms arose, atoms emerged, distinctions between atoms arose. I should actually say fundamental particles arose, emerged, and then atoms arose. And then atoms combined together to form molecules, and there were distinct molecules, and there were higher order molecules and cells and so on. That is the history of the universe. And whatever gave rise to that process of emergence of structure, emergence of distinctions, that is what a large number of people call intelligence. It's simply the self-organization properties of the universe. And this is what Prigozhin called, in using the Sanskrit word, Leela of the universe, because we don't fully understand it, but we understand it in terms of some properties of the universe. And biologist, what's his name? I've forgotten. Waddington, sorry. Yes, Waddington pictured this in terms of what you call epigenetic landscape arising from a set of constraints. Constraints at the level of the universe, constraints at the level of life, constraints at the level of each taxon. And each constraint gives rise to a particular set of pathways for life to evolve. So what I'm trying to point to is a theory of evolution in terms of constraints. Constraint randomness is what I am pointing to, not simply randomness, not completely random, not completely deterministic, but constrained randomness, which is exactly what Waddington had in mind when he proposed the theory of constraints. There is no supernaturalism here. So are we agreed on that one?
I deeply worry about starting out with notions of intelligent design. So in the first place, a straightforward disavowal. I don't understand physics, even Newtonian physics, leave alone quantum or Einsteinian physics. So I'm not going to speak to that. I will restrain myself to the little mundane realities such as, for example, SARS-CoV-2 mutations and stuff like that, and their selection and quote evolution in quote or microevolution that I understand at least a little bit of. That said, I'm very uncomfortable with using the term intelligence in what frankly sound to me like quasi-mystical terms. Because for me, the primary distinction that's at stake here is between intentionality versus emergence. Is there a prior intention to achieve a certain downstream outcome, downstream of the cause and effect chain, or is the outcome, no matter how beautiful it looks, I'm putting the word beautiful in quotes, no matter how beautiful it looks, an emergent property rather than being an intended property? And that for me is a crucial distinction, and I'm arguing that intentionality is neither conceptually nor empirically valid.
Yeah.
And what is therefore valid is the emergence of patterns. And as far as I can tell, all that Waddington and even more idiosyncratic Darcy Thompson before him were talking about is that you will have evolution between patterns, and then you will have evolution of more complex patterns, and you will have evolution amongst more complex patterns. And this is simply, in a very odd sense, this is simply a Marxist view of historical trajectory, of how relationships lead to more and more complex patterns of relationships. So in that sense, sure. But it isn't apparent to me that this is the crux of the Darwinian argument. As far as my very lay understanding of that argument goes, it simply suggests that there is unintended, as far as outcomes are concerned, unintended variation at the heritable level. And in that unintended variation, there is natural selection operating. That natural selection is locally contingent and can change, and therefore does not have a predictable trajectory over the long term. You don't have the same natural selection over and over again. You can have catastrophic alterations and so on and so forth. So those two components, that there is an unintended, and in that sense random, variation in heritability, in heritable components, and operating on that there is a natural selection pressure, is, as far as I'm concerned, the Darwinian contribution to my explanatory model. So I am not speaking of theory. I'm simply bringing up here what I learned from Darwin. And this is what I learned from Darwin. So what I learned from Waddington's argument is at a completely different level of organization. What I learned from Waddington is at the level of how, when an individual organism, which is the base unit of heritability, it's the point at which inheritance is going to happen, in a sense, is going to go from one generation to the next generation. In that individual, how is the unintended variability likely to be patterned and constrained because of the rules of morphogenetic design, of body design? That's the Waddingtonian epigenetic landscape. And for me, that provides an explanation that just fits very well with what Darwin taught me. So I don't see these as competing theories which I need to even position against each other in order to enrich my understanding of the historical trajectory of the biosphere.
Okay, I think let us formulate it this way. What you have done is to identify what we mean by Darwinian evolutionary theory as a kind of core proposal, the central proposal of evolutionary theory. Fair enough. Okay. Then where are the differences? And you pointed out earlier that the differences might lie in the mechanisms that we specify. And even in the case of mechanism, it could be the case that we might need some additional mechanisms that we have not proposed yet. And I'm perfectly happy to say, well, let's think of it as additional mechanism, in which case there is no contradiction. Contradiction happens only if you say these and only these are the mechanisms. If you say that, addition would be logical contradiction. But if you say these are some of the mechanisms, we can bring in some other additional mechanism without any contradiction, and that will be addition, not conflict. So what you're suggesting is that perhaps it is better to view this as not in terms of logical contradictions. Formulate your theoretical propositions in such a way that other things can come in without contradiction. So never say only these and nothing else. That becomes a problematic case. In the way I function in theory construction, I tend to make the strong claim looking for contradictions. This is a different style of functioning. It's not necessary. You might say this is the MIT style of functioning because we thrive on debate.
I was about to say that.
So I'm perfectly happy to take a slightly less gladiatorial, gladiatorial approach to theories. Fair enough. I mean, it doesn't really matter as long as the statements are clearly articulated. So in which case, the point I would like to make is to do with the causal mechanisms that are needed in constructing an evolutionary theory. And you defined, interestingly, random in the sense of unintended. Fair enough. I think we both agree on that. I mean, when I used the word intelligent, I wasn't suggesting any intentionality here at all. I was using the word intelligent in a particularly secular sense, in the sense in which, for example, Wolfram uses it, which hardly has any intentionality, as any mystical quality about it. Simply hardcore science and hardcore mathematics. So emergence is the crucial part. As I see it, the Waddingtonian enterprise is really based on constrained randomness or constraint emergence. As evolution progresses, more and more constraints emerge, and these constraints are retained. So let me define randomness in the probabilistic statistics probability sense. So if you say a fair coin, the outcomes are equiprobable. If you have tail and heads, then it will be 50-50. If you have a dice of 6, all of them are equally probable. That's a sense in which we use random in statistics probability theory, not in the sense of unintended. Okay, so let me use the word random in that sense, and then ask, is mutation, that means mutation means change, is change in evolution random? So in fact, it is well known in biology that biologists accept that it is not really random in the statistical sense, because people recognize hotspots where lots of mutation happen, and things which are completely preserved. So there are certain areas of the genome that you are not allowed to touch. Okay, what happens when there is a mutation in those areas? Well, there is this repair coming in, the other mechanism coming in and repair it before you move from DNA to protein. Those so-called errors are repaired immediately and changed. So there are constraints at that level before you go from DNA copying to proteins. Then when proteins emerge and the proteins kind of construct cells, if there are defective proteins, they don't enter into, for example, if the proteins don't fold, then they cannot function as proteins. Or if they are badly folded, then they cannot participate in the cell formation. So those proteins are eliminated. So elimination, if I'm thinking about selection as not as selection, but as elimination, there are constraints that eliminate bad options. And you come to the cell. And as you proceed, though these are well known to biologists, I don't have to belabor on that. But the point is, I'm pointing out that implicit in this view of evolution is the idea of constraints. It is severely constrained all the way. And all these are called viability constraints. And by the time you come to the fecundity, that is time for reproduction, a whole bunch of stuff has been already eliminated. It is severely restricted. So I'm talking about really constraint and repair-based account of viability. Before you come to the reproduction gate, these are eliminated. So if you have, for example, a gene that, let's say, mutates, and the cell membrane is not produced, right? You are eliminated right from beginning, because if you cannot create cells, you are out. So these are the things which are persistent all the way from bacteria to humans. So if you look at that, if you have a mammal and then you don't have vertebrae, obviously you cannot exist. You are not even born, all right? So there are many of these things all the way from DNA to reproduction. There is a several stages where things are eliminated. So by the time you come to reproduction, what you have is a very small set of possibilities of mutation, and that has to be a theory of constraints and repair. That's my main point.
So
that's a mechanism.
So here's a response of sorts. Let me use what Siddharth Sharma has said in the chat box in conjunction with what Mo has said. So in the first place, it seems to me that you are defining the processes of evolution necessarily as things that happen after an organism is born. I tend to think of everything else that you are counting as getting eliminated as part of the processes of evolution. So there are two components to that. Number one, when does an organism have to cease to be viable before you accept that loss of viability to be part of the evolutionary process? As far as I'm concerned, it can be at any point. And therefore, if there is a, quote, mutation, unquote, that's a lethal mutation for a cell, that loss is under evolutionary pressure.
Okay.
Non-viability of that kind itself is one version of evolutionary pressure, of selection pressure, number one. Number two, because the alternative leads me into peculiar arbitrariness. So, for example, do I have to wait to be born before I die and contribute to evolutionary selection? Why? And then at what point? And then is a premature death part of the evolutionary selection process, or the pre-evolutionary Waddingtonian constraining? All of this becomes more and more arbitrarily confusing for me. So in a sense, to connect to what Siddharth Sharma is saying, the argument for me is that processes in vivo, as he puts it, are actually processes that function in the broader rubric of evo.
I agree.
So it's in that sense that I don't even think that the evo-devo, which I agree with him entirely, is a major change of the 20th century, last century, 20th century. Sorry, I am very much 20th century, so I still think in terms of that. So is very much evo-devo, but I don't think that it arose out of logical contradictions. This is where I'm not disagreeing with Mo. I keep entering persistent caveats that I don't think that it's a contradiction. I think it's an enrichment. It started out as an enrichment, and it's continuing to be an enrichment. We've learned how the mechanisms of developmental morphogenesis have provided the terrain of selection processes that we can actually see in operation, as opposed to selection processes in the biosphere, which are not, time and space-wise, not necessarily easy to see. So that's my second point. And I add Garvit Bansal's point to this, that constraints form the shaping of what I'm calling the unintentional variable pool of variation. But the factors that operate to select on this pool are a whole separate set of categories, not a single category. He's pointing to some random events, and they're not all necessarily that random event as an asteroid strike or something. They can be, emerging out of other patterns, so to say. In a biosphere, you may have properties such as savannification, such as desertification, which are driven as an emergent property of the biosphere sometimes, that in turn feed back as selection pressures. So absolutely, the unintentionality is the crux of the matter, coupled to what I'm calling the heritable variations that are unintentional. So that's what I keep coming back round to.
I think so far in most of the things that we have talked about, we unfortunately tend to agree. I was looking for some.
So maybe we should bring in the audience to provide that.
But let me just say this. I think you are agreeing that one of the mechanisms is that of the selection at various stages, the viability selection, which you include under selection pressure. But in order to understand that, I am only suggesting that these should be explicitly articulated as constraints, so that evolutionary theory will have a set of constraints to understand evolution. So I don't think there is a disagreement there. I am simply suggesting a methodological strategy to set this up in terms of explicit constraints, which I can see you have some reservations about, and that comes from our styles of functioning. The kind of theory construction that I'm used to, goes for explicit articulation to check if the predictions are correct and looking for counterexamples and so on. But that's a separate issue. I think we should probably. I was also planning to talk about the theory of habitat and theory of adaptation. Theory of fitness are different, but those are things that can be taken up later. We have already exceeded our time limit of 30 minutes, so we should now leave it open for questions. Okay, so I am assuming that Sabarish would take care of.
Yeah, so if the participants have any questions, please put them in the chat box. Also, Mohan, Satyajit, would you want me to go over the questions that are already there in the chat?
So I suggest that Siddharth Sharma's first point is directly for Mo, since what Mo referred to as intelligence is, as to quote Siddharth Sharma, just laws of physics. There is no difference between them, and maybe Mo should address that.
By intelligence, I didn't mean laws of physics alone, but something more than that, the kinds of things that people like Prigozhin have talked about, principles of self-organization. So let me state one such principle. One of the principles of self-organization is combine two things to form one unit, combine different particles to form one atom, combine different atoms to form molecules, combine different molecules to form cells, and so on. So combination is one of the principles of self-organization. It's the people who are looking at self-organization who have identified these things. They're not part of classical mechanics or relativity theory or quantum mechanics, but at a higher level. People like Stephen Wolfram are doing that. The other is diversification, differentiation, not simply putting together, but differentiation. Whenever you have things, atoms being born or emerging, you also have different kinds of atoms, different kinds of molecules. So there's a differentiation and combination happening in the history of the physical universe, but the same thing happens in the biological universe as well, and in the cultural universe. So I'm talking about by intelligence, I mean principles of self-organization, and I'm going by not just physics, but the kind of work that Prigozhin did in order out of chaos. How does structure come to arise in the universe? Structure at the level of physical reality, at the level of biological reality, at the level of mental reality, at the level of social reality, and so on. That's what I have in mind, not just physics, much more than that.
So let me press back on this and again pick up on Siddharth Sharma's most recent response point, that the principles of self-organization seem to him to emerge out of simpler laws. Again, I do not speak of physics, but simply listening to Mo, it sounds to me as though you're pointing out that there is a common thread of self-organization, of pattern formation that you're referring to as self-organization, but at different levels, the underlying mechanisms that lead to pattern formation are likely to be quite different. You referred to cultural pattern formation, and the underlying mechanisms that lead to the formation of patterns in culture are likely to be quite different from the underlying mechanisms, the nuts and bolts mechanisms that contribute to pattern formation at the atomic level. So in that sense, then, pattern formation simply becomes a conceptual category more than a mechanism, it seems to me.
I think that is a way of looking at things. The way I look at this is there is an abstract transdisciplinary component, and the manifestations of that abstract component will be different in two different places. So obviously, the way the laws of combination apply, the propensity for combining things to form high-level units would be different at the molecular level, at the cellular level, at the organism level, and so on. Sure, but there is also a homology. So the whole idea is that there are certain strong similarities across the board. There are also differences. So if you think of this as kind of manifestation, so there is a core component that is the same in, let us say, graphite and carbon. Of course, graphite and carbon are different, but at the same time, there is also an underlying core that is the same. So I'm talking about that sameness, different manifestations of the same thing, and I'm focusing on the sameness of things, what physicists would call symmetry, and not the transformation part. So these two things come in pairs. I mean, they are two sides of the same coin. You cannot do one without the other.
So let me push this forward, based again on the chat comments, that for Misel's and the spherical geometry of the sun, self-organizations can be traced to simpler laws. And all of this is true, of course. But Nagananda's point is the distinction. This is addressed to you, Mo. The distinction you're making by alluding to self-organization looks to me like a standard reduction and emergence argument. I think it's misleading to call it intelligence. Emergence can be a more familiar and appropriate term. Since I'm absolutely refusing to get into anything other than my ordinary terrain of biology, I'm simply not.
I think for the purpose of this, this discussion, what is causing the trouble is the English word intelligence, not the idea, but the word. I'm perfectly happy to, take away the word. As a linguist, we don't care about the words as long as we define them. But the word intelligence creates unnecessary emotional problems. So let me call it alpha. All right. So you will ask me, what do you mean by alpha? What I mean by alpha are the constraints of, self-organization.
So my again, not disagreement, but caveat on it is that, as I pointed out, because I see the contributory mechanisms, what I keep calling the mundane nuts and bolts mechanisms that lead to pattern formation at different levels to be quite different. So, for example, the SARS-CoV-2 virus spike protein, its folding is a self-organization constraint, and some mutations will permit it, some other mutations will not permit it, and that's sort of at issue here. But the underlying mechanisms are to do with the atomic and molecular rules, the biophysical rules of protein folding. On the other hand, whether SARS-CoV-2, a certain virus variant, will transmit more efficiently versus another variant will transmit less efficiently or not, and how certain variants as a group will begin to transmit more efficiently is again a pattern. And that's a self-organization pattern. But the underlying rules and mechanisms that lead to the emergence of that pattern are quite different from that controlling the spike protein folding. And as a result, I'm not sure that I am getting anything terribly worthwhile as an additional insight by including the idea of propensity to pattern formation in how I think about the evolution, the microevolution of the virus, for example. So while I grant the idea, I'm not sure I see the value of the idea in and of itself for contributing mechanistic insights, for contributing nuances of causality.
Let me see. So I'm trying to figure out whether I should respond to that or respond to a student. But let me very quickly say, I think the idea of what is underlying and what is a manifestation, we may have a different takes on this. Let's take something like the idea of force. The idea of force in classical mechanics is very specific. Force is that which changes velocity. Okay, every change must have some causal component, and that cause is called force. But then if you take that thing to, for example, intermolecular forces, the force is not exactly that of change of location. You could think of it as change of location. You come to, for example, electricity and magnetism, there is repulsion and attraction. In gravity, there is no repulsion. Well, at least in classical mechanics, there is no repulsion in gravity. So the way the force, the concept of force works in different cases for emergence are different, but there is a core idea of force and differences in the manifestation of force, different kinds of forces. By understanding the nature of the relation between force and change, force as a cause of change, we have a theoretical tool a theoretical tool that you can use all the way from subatomic physics to forces of culture. And it's a single transdisciplinary construct. And now what you're talking about is the nitty-gritty details are different. Of course, they are different. So the reason why I'm saying this probably is because of my own history as a theoretician. The way we do this in linguistics is we construct theories of grammars, individual grammars, and then we explain those grammars in terms of universal principles. So we see individual grammars as the resultants of emergence of this kind, but the details from one language to another, they are different, but you also see the effect of the universals. Now, it is very hard to appreciate that until that kind of theory is fully worked out. I can show you the effects in linguistics and convince you that the idea of universals is essential in understanding human language. But to show its parallel in biology, I have to work out the equivalent of what Chomsky did in biology. So I think you are not convinced because the theory of universals in biology has not been worked out yet. But you cannot work it out unless you have graduate students who are willing to try it out. So what I'm suggesting is that unless graduate students are willing to take the risk of trying this out, and maybe they discover finally that it is not doable, or maybe they will achieve a huge breakthrough. It is only then that we can actually discuss whether or not this will lead to greater insight or not. For that to lead to greater predictable, rigorous, kind of insight, you need to work out the theory. Theory doesn't exist yet. So how can you demonstrate that this is a better theory? So I'm just, at this point, I'm only speculating.
Fair enough. So we will leave this particular point there, and we will shift to a couple of other points. Let me pick 2 points that I will make comments on, and then come to Aanchal Saksena's point, which I think I would like to hear what Mo thinks about it. So Vigneshwar Ramakrishnan is asking, intelligent design proposes constraints as the way how evolution happens. And I'm afraid that's not what Mo said. Mo simply pointed out that intelligent design proposes constraints not as the way evolution happens, but on the way evolution happens.
Yeah. Yes.
So
whereas
Darwinian theory proposes natural selection as the force leading to evolution, and Mo has no problems with this selection as the force. And therefore, in that sense, while you think the two theories are quite different, Mo's theory of intelligent design is actually not that different from, is not a contradiction. It's an enrichment. Okay. Which was the point I was trying to make. Simply adding to that, again, Vigneshwar Ramakrishnan asking me specifically, in the case of SARS-CoV-2, only certain mutations happen and others do not. This is constrained by the biophysical principles, as you say. I don't see how Darwinian aspects come in here. Let me point out 2 things. In the first place, mutations happen or don't happen because of 2 different reasons. When we say, you see, accuracy matters. When we say mutations happen, we really are talking about mutations happening in the sequence, but we are actually implying what happens at the amino acid level, at the level of protein folding. But there's a gap here. So mutations happen or not happen is driven by DNA secondary structure and whether they are hotspots or not hotspots for errors and so on and so forth. And that is driven by historicity, by the sequence, by the secondary structure, all of which are what I keep calling unintended prior structured patterned baggage. And that, I agree, is not selection driven at the time that it's happening. And therefore, I agree that mutations happening is not necessarily under selection pressure. But when we talk about my loose usage of that phrase was in response to Mo's point about how certain proteins don't fold. And proteins not folding, I suggest, is actually a selection pressure. Because when a protein does not fold properly, the life form that protein is dependent on loses viability. That's selection. So I'm making a distinction here between when mutations happen or don't happen at the level of the sequence during replication or during copying. And that is an example of unintentional patterning, constrained randomness, as Mo would call it. And I'm pointing out that if you simply move one step further and think about protein not folding or folding, then you immediately invoke selection pressure. And I wanted to point this out because it makes a very interesting juxtaposition of constrained randomness on the one hand and selected evolution on the other hand, in a very narrow example of mutation at the level of the nucleotide versus mutation at the level of the amino acid. But let me move to Achal Saxena's point, which let me quote the earlier one that she began with. Are there constraints that seem to influence evolution more than other constraints? Or do all constraints have an equal effect? I think this is a great question. and I'm kind of hoping that Mo will take this on, because I'm still trying to wrap my head around the question.
Okay, first of all, let me say that Satyajit talked about proteins folding properly. That's a great expression. The way I would formulate it, as in given my predisposition to construct theories of a certain kind, I would say that should be governed by what do we mean by a grammatical protein and an ungrammatical protein. A proper protein is a grammatical, structure. The other one is an ungrammatical structure. And the way linguists, for example, would approach this is to say, what are the rules or what are the constraints governing grammatical proteins that distinguish them from ungrammatical proteins? We want to be very clear, state them in gory details, explicitly. So that's the kind of theory construction that I was advocating. So the difference is in terms of the degree of rigor and explicitness in formulating what Satyajit called proper folding, proper cell, proper heart, proper whatever, so on. Now, to go back to the different kinds of constraints, if you look at the way things have persisted, if you think of evolution in terms of not only elimination but also persistence, what are the kinds of things which are persisted? You'll find that there is an asymmetry. The initial kinds of constraints are extremely strong; they are inviolable. The constraints that apply at the level of cells, for example, the constraints that apply to bacteria, cells in unicellular organisms as well as in multicellular organisms. As you proceed to constraints that operate at the level of animals, notice that the constraints on animals could not have existed before animals existed. So these are emergent constraints. So as we proceed in the flow of evolution, the older constraints become more and more stabilized. They're inviolable. But some of the newer constraints are kind of violable. And by the time you come to, for example, the human level, that is where evolution can happen. So essentially what evolution is saying is that don't mess up with some of the old constraints that I formulated earlier in the history of life. But you are free to violate some of the new things. That's fine. That's where experimentation or the mutation happens. So there is a degree in the what you might call in the plasticity of the constraints that the constraints allow. Some of the constraints are more tolerant to changes, but some of the older ones are absolutely rigid. They have been fossilized. You cannot touch them. So if you look at that history, you can see the gradation of the rigidity of the constraints, inviolability of the constraints. As you proceed, more and more constraints become more and more viable. So in some cases, for example, it may be the case that you have legs, and then you might think that having legs in the case of, for example, lizards is inviolable. But there might be cases where you lose your legs. That happens in the later history of the biological systems. So you cannot, the inviolability of constraints becomes an issue. I think this is what Anshul is talking about.
So, I'm going to punt on this one because, as I pointed out, I'm still trying as a biologist to wrap my head around the notion of are there categories of constraints that are more likely to influence evolution? Are there categories of constraints that are less likely to influence evolution? And so I'm going to simply say, I don't know as yet. I got to think about this. But having said that, let me add a sort of postscript to my punting. And that is, I don't think it's useful to forget that there isn't a common directional trajectory to evolution. And a component of this is, Mo said that what I mean by proper folding should be defined by a set of universalities. And my response to that is not so much to provide those universalities, which I don't have. I am, this is essentially an ancient Indian debate between Shankara, who is bent on his Advaita, and all the rest of the empirical Dvaitins in the system. And clearly Shankara has triumphed. So don't worry more. But
wait. I think he is logically contradictory. Anyway, that's
so of course he is. But here is the issue. What do I mean by proper folding? And I pointed out what I meant by proper folding as a contingent property.
Yeah.
All that proper folding meant was a viable virus particle emerging or not? If a viable virus particle is emerging, it doesn't matter to me whether some universal property of proper folding is fulfilled. An associated issue in this is, again, let me point out that a given mutation is not lethal equally on all genotypic backgrounds. You can have the same mutation, for example, kill a virus. You can even have a human cell line in which one mutation will kill the cell. But if you have selected the cell in under certain conditions where the cell is not even mutated, but simply epigenetically, for example, making larger amounts of a particular chaperone protein, that mutation which would have killed the same cell under other circumstances is not only no longer killing that cell, but that mutation may enable certain biological functional outcomes to be emerging. And it is this degree of situational contingency that for me repeatedly points to the, shorthand, Darwinian argument of contingent situation-based selection as the constant shaping of emergent patterns. And really, that's the point I'm trying to make. So there's a little question here. Hang on. So Darwinism, Siddharth Sharma is pointing out, Darwinism comes into play when you talk about how these mutations are selected, and I agree with that entire sentence, except that I don't use the term Darwinism. It's simply an idea that old man had, which is very useful. Isms is a bit much. But can we view, here's the interesting question, can we view selection as one type of constraint? And in that sense, Darwinian theory can be subsumed by Mo's intelligent design theory. The word intelligent still sticks in my throat, so I ain't swallowing that. But let me present that as the other way. The Darwinian argument is perfectly welcoming of all sorts of non-selection constraints anyway. In fact, he didn't know anything about other constraints because we didn't know enough biology in the 19th century, as has been repeatedly pointed out. Sure. So over the past century and a half and past century and 3/4 now, almost by now, we've learned all sorts of levels of organization at which constraints of historicity, constraints of pre-existing patterns shaping what patterns will form, and what patterns might form in different biological forms will come up. And all of that, for me, simply enriches our understanding of the original notion that we started this conversation with of evolution, and trying to figure out what mechanisms would have contributed to this process in what configurations. And really,
let me hasten to add, in some of these questions, there is a probable presupposition that I'm an evolution denier. Hardly so. I am an evolutionist, if you wish. The conversation.
But Mo, you might want to address that last question.
Yeah.
Can you please elaborate on why you think Darwinian evolution and intelligent design as only theory seeds and not theories? Because that's very much a question for you. And what you think of what consequences the distinctions you're making by qualifying randomness have on predictive power. And that's all yours.
Yeah, there are many points that I would like to address. I think this one is theory seed versus theory is the following. A theory seed doesn't make any testable predictions yet. A theory, on the other hand, makes predictions, that is to say, so you need not just one proposition, but many, many propositions. And when those propositions are put together, you deduce predictions. It's like saying a mathematical theory is not simply one statement, but a collection of definitions and axioms. It is only when all of them are put together that you can deduce a theorem. The same thing applies to scientific theories. So a seed is simply one of those crucial central propositions. But then that has to be supplemented with a large number of other propositions from which you can deduce predictions and you can test the predictions. That's the distinction I'm making. Okay, so to go back to some of these issues, I would like to suggest that instead of using the word selection, it kind of suggests selection from the top. Let's use the word elimination, and let's formulate this as the unfit are eliminated, instead of the idea of survival of the fittest, which is how Darwin saw it in natural selection. He saw natural selection and survival of the fittest as being synonymous. And there is something that is odd about the notion of survival of the fittest. What that means is that you're comparing many candidates and you select the one that is the best one. Instead of that, I'm suggesting you don't do that. You have a criterion of fitness, by which I mean ungrammaticality, grammaticality and grammaticality, and you eliminate things which are ungrammatical. This is a theoretical linguist speaking, trying to draw upon a different domain. If you do that, you need a theory of fitness. That is where you have a set of constraints. So there was this question, are there different kinds of constraints? Yes, there are some fundamental functional constraints that apply to all forms of life. These are not anatomical structural constraints, they are functional. So for example, there has to be some mechanism for taking in nutrients and building structure inside. There has to be some form of internal transportation. There has to be some way of reproduction, and so on and so on. You can identify something like, 9 or 10 or 12 or 15 functional constraints, not structural, not anatomical. This applies to all forms of life. And when you come down to more and more evolved distinctions and so on, there are constraints that apply to animals, which do not apply to plants. So animals must have a kind of central food tube. Now, notice that we are now moving on to constraints which are kind of function and structure together. So those mutations which change the structure but violate any of the functional constraints would be eliminated. This is not a question of selection, but elimination. So I'm trying to draw a different kind of picture for constraints. Constraints which disallow certain kinds of things, not select certain kinds of things. That gives you a very different way of constructing theories. I'm interested in pointing to certain methodological strategies for theory construction. So it is not really an attack on Darwin. I am perfectly happy to, as I said, I am a Darwinian myself, but this is like saying I am a Chomskyan myself, but then I have fought with Chomsky all my life on the details. So it is the details where we have disagreements on. The same thing applies to Darwin. Our fundamental principles, yes, absolutely, no disagreement. But I'm suggesting a different set of methodological principles of formulating the patterns as constraints, explicit constraints, such that we can deduce predictions, and formulate the constraints as elimination. If something doesn't satisfy the conditions on fitness, you eliminate them. And some of these conditions could be the relation between different levels within the organism. It could also be the relation between the organism and the habitat. If those correspondences are violated, you become unfit. So, for example, if fish requires, ability to absorb oxygen underwater, but if you put a bird inside water, the bird dies. If you take the fish outside of water, the fish dies. And these are fitness characteristics. A bird is fit only in the outside of the water, and did I say that right? Yeah, okay. And fish is fit only within that habitat. So we have to formulate these constraints on the relation between organism and the habitat. That means you have to have a theory of habitat, you have to have a theory of the organisms, and a correspondence rule, which is a constraint on the relation between the two. Notice what I'm talking about is how to construct theories, methodological strategies for constructing theories. And that is where this notion of constraint randomness and constraints at different levels, and constraints as contingent, in the sense constraints have been emerging themselves. Constraints on animals could not have existed prior to the emergence of animals. Constraints on vertebrates could not have emerged before the emergence of vertebrates. So these are things which emerge. They are contingent constraints. But those contingencies are shaped by functional constraints at the universal, at the level of life in general. I assume that I have kind of responded to many of the points raised. I'm not sure.
So let me make a little quibble. I suspect that survival of the fittest is not a phrase that the old gentleman himself used. I think it's a phrase that some of his defenders used, and somebody might want to do Googling and...
No, it is Darwin used it. In fact, somebody suggested this phrase to Darwin, and he happily accepted it.
Secondly,
yeah.
Again, being, if at all anything, an empiricist, I think about this as in very empirical terms. So COVID-19 and SARS-CoV-2. Think about it this way. There was this conspiracy theory floating around that the virus has been engineered to be optimally transmitted, infecting human beings. And if anything we have learned over the past year and a half, it is that the virus ain't done learning how to spread amongst human beings. Because there are mutations, and because it's spreading a lot, there are lots of variations available as a pool of variations, and therefore selection pressure is simply leading to more and more human infectious virus. But here's the empirical oddity. Early last year, it became apparent that the virus could infect European mink on mink fur farms. Mink is a civet family member that's farmed for fur. And the virus could infect mink, and in fact, mink could transmit it to each other. And in fact, lots of mink got very sick on mink farms. Mink farms had to be eliminated, like poultry farms were eliminated with bird flu scares and so on and so forth. Here's the interesting experiment that nobody's done, although I've been asking about it. We have the Delta variant, which to all appearances has undergone selection pressure and has emerged as this better survivor in a global situation in the human community where distancing has led to a reduction in transmission efficiency for the virus, therefore a more efficiently transmissible virus variant has gotten selected. Is the Delta variant also better with mink? Or is there in the mink community a whole different trajectory of fitness altogether that is leading to a whole different emergence of more fit virus variants? And I use that as an example to point out the extraordinarily granular contingency of selection. Now, that leads me, of course, to agree completely with Mo when he says that we need to be considering habitat and what I think of as the microenvironment at a variety of levels in which selection is taking place as an ineluctable component of the evolutionary process. But I am pointing out the extraordinarily contingent nature of these directions of selection for fitness. And it's because of that that I tend to agree that I don't see, as a non-evolutionary biologist, I'm not getting into theories of fitness. Evolutionary biologists have theories of fitness that I don't understand, and I am not defending those. But I am not in disagreement with the argument that it's very hard to do any long-term prediction of evolutionary trajectories. All that I have seen done is really very, 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 very short-term predictions. And I suspect that that's to do with the extraordinary emergent contingency of selection environments.
Satyajit, we may have a different meaning for prediction. Let me check if that is the case. When I use the word prediction, I don't mean something that is going to happen, but also the past. So all the data that is available about the past, they're all subject to prediction. Prediction is, not just future, but also past and present, in particular present. It simply means logical consequence, as in the case of, for example, a mathematical theorem. And that also takes me to use of words like selection pressure. I resonate to that word, selection pressure, but what I'm looking for is a theory of selection pressure in terms of clearly articulated propositions so that I can deduce the logical consequences. And if I cannot deduce the logical consequences, that is the predictions, I don't know how to evaluate that word. That's simply a word that gives me a feeling of understanding, but not rational understanding in terms of testable predictions. This is what I meant by theory seeds. So natural selection, selection pressure, all these are words that point you in the right direction, but then you have to convert these words into testable theories that give you testable predictions. The same thing applies to fitness. The same thing applies to adaptation. All these I see as promising words, promissory notes, but I want to see the theories completely fleshed out so that I can critically evaluate them. And critical evaluation means looking for counterexamples. What are the counterexamples? If such and such counterexamples existed, would I say I have to change the theory? If I don't get an answer to that question, under what conditions would you say your predictions are wrong? I don't know how to evaluate a theory. So I need all these theories of fitness and selection pressure and, all those things. Those are the things that I'm missing. And so I'm actually arguing for, I'm not arguing against Darwin. I'm arguing for a certain methodology for theory construction to convert Darwinian ideas, I still call them ideas, not fully fleshed out theories, ideas into fully fleshed out theories, and if possible, formal theories. As in, for example, this is something I know that you would disagree with me on, in stating these laws, constraints as laws, as in Newtonian F is equal to ma, or such things. And I can see immediately the horror of the what shall I say, differences between the community of theoretical linguists and the community of biologists. We have different ways of thinking about theories. But well, I would like to have formally expressed theories. I don't mean mathematically expressed. It could be in terms of formal logic, doesn't matter, but clearly articulated such that you can deduce the consequences in a straightforward fashion. Yeah,
I understand, and this is why I started out by saying that I tend to think about all of these much more modestly as explanatory models. But what you might want to do, Mo, is read the last comment from Nagananda and respond to that.
Yes, not well-defined predictions, but predictions which can be tested against observational generalizations. And if there is a conflict between logical contradiction between predictions and observation generalizations, then that prediction is supposed to be false. So I need to look for, identify, deduce all the predictions and test them against observation generalizations, see if there are logical consequences. I also need to know under what conditions would the prediction, would you agree that the prediction is false? So you have to say something like, if such and such observational generalizations turned out to be true, I would admit that my prediction is false. So this is the crucial aspect of scientific theory constructions. You look out for counterexamples, actively look out for counterexamples. And you, to the extent that you cannot find any counterexamples, but you did a good search, you say, okay, I haven't been able to find any counterexamples yet, so I'm provisionally happy to accept the theory. But of course, you say, maybe I'll find something 5 years from now. So when I did my PhD thesis, I was quite happy there were no counterexamples. And I said, that's a good theory. 5 years later, I found myself lots of counterexamples, and I argued against my own theory. I started giving talks against my theory. This is a crucial factor, crucial characteristic of scientific theory construction. You look out actively for things which would show that your predictions are false. And for that, I should be able to deduce the predictions mechanically. That's exactly, yes, Nagananda, that's exactly what I meant by saying, making the distinction between theories and theory seeds. Theory seeds are promissory notes, but they haven't been fully fleshed out as trees.
So let me take Achal Saksena's point about adaptability. And what about adaptability? Over a really long time, wouldn't that affect the constraints that tie an organism to its habitat? Absolutely, yes.
Yeah.
Let me introduce a caveat. When we think about adaptability, it sounds really nice because surely adaptability would be a great advantage. Especially as conditions, selection, environments vary constantly, adaptability would be great. The trouble with that notion is that I am, again, not as an evolutionary biologist, but as an empirical molecular cell biologist, physiologist, I don't know an example, an actual real example of adaptability without costs. When a mutation provides adaptability in the sense that progeny might survive better under a more diverse set of environments, it is almost invariably at the cost that that mutation in that particular original environment competes a little poorly with a genotype that does not have that mutation. And if that's the case, then the selection of adaptability is dependent on a constantly changing environment. In other words, if the environment stabilizes over a long period of time, that's in some ways going to be a selection pressure against the property of adaptability. So I don't think that we should be thinking about adaptability in some immutable fashion. It's simply, for me, another biological property that will that will play with selection pressures of diverse kinds.
I wonder if what Anshul means is something like the wider or narrower range of fitness with the environment. So if you compare, for example, humans with bacteria, bacteria have much wider range. They can survive in all kinds of environments. Different kinds of bacteria can survive in all kinds of, even without oxygen, or in some cases, oxygen is toxic for bacteria and so on. In the case of humans, our possibility is extremely narrow. And that is the price that we pay for growing structurally more complex. But then there are also cases like my favorite example is koala bear. It's completely adapted to a very narrow domain, eucalyptus. If those trees are destroyed, then koala bears would become extinct. And if they don't have the capacity to adapt, by adaptability, if you mean something like plasticity of changing your habitat, then it is deadly. So it's a price that you pay. To avoid competition, you behave like a koala bear, but you can also behave like bacteria to survive in all kinds of conditions.
So Madhu's just written a comment that actually says what I meant to say better than I said it. So, but the question, as a question, it is directed at you, Mo. So let me just read the question and you can respond to it. One aspect that could confound theory construction in evolution is the consideration of the environment. Fitness is adaptability or suitability to this environment. And since this environment keeps changing, what could be an unacceptable and unselected mutation in one environment may be the opposite in another environment. And the earlier example of misfolded protein may be advantageous under certain environments. The key question is then, how does a theory account for a changing environment? And you might want to...
Yeah, the way I look at a theory of fitness, a theory of adaptation in terms of habitat is simply by building a classificatory system of habitat. So you begin by formulating the broadest possible range of habitats. For example, habitat of water, underwater, habitat of surface of the earth, habitat of under the earth. Let's say I'm just constructing this theory in a broad sense. And then you see the way organisms fit in these environments, and you find that some organisms survive underwater, some organisms survive on the surface of the land, some organisms can survive under the earth. And now you begin to bring in another factor, namely temperature. Some organisms survive only in certain range of temperatures. Humans are a classic example. If the temperature increases or decreases, humans become extinct. If the entire earth were like that, beyond that temperature or below that temperature, humans would die. The same thing applies to other kinds of creatures. There are other kinds of things like nutrients, availability of nutrients. If certain kinds of nutrients are not available, then the species would become extinct. So what you need is essentially a theory of an inventory of habitats and their classificatory system, and a theory that tells you, given such and such anatomical and functional properties of the species, they are best adapted to such and such categories of habitats. But that theory has to be constructed. I'm not saying that there is a single, notion of adaptation. Is simply the correspondence between the organism and its habitat. So that I'm looking for a theory of that kind, which has to be constructed. Again, my plea is for explicitness of the propositions about the categories of habitat and the subcategories of habitat and their correlations with the properties, anatomical and physiological properties and behavioral properties of the organisms. That's when you see a theory of adaptation. Otherwise, adaptation is just a word. It's not a theory.
So let me since we don't at the moment have a comment, let me annoy Mo publicly.
Okay, let's try.
Let me use this what Madhu's question was and what Mo said as an opportunity to be annoying, and that is the reason why empirical biologists may be impatient with formal categorizations of, for example, habitats, or what, to use Madhu's word, environment, the selecting environments, is that selecting environments don't classify in any meaningful or empirically useful fashion. The problem is we can't come up with a list of attributes of environments that are definitively separate from each other, because as Madhu pointed out, the sheer degree of entanglement and conflation going into selection configurations is so high that we don't know how the hell to do this. So what we are simply doing is responding to what we see as the granular reality. And so the annoying question is, what will a formal theory give us that we don't currently have?
A theory.
That's just a word as far as we are concerned.
What it means is this. You're using
That's just a word as far as we are concerned.
I know. Let me explain.
It gives us an instrument to explain something better than what we are doing today.
So when you say empirical, scientific theories have to be empirical. What you mean to say is the research at the level of observational generalizations. Now, you need observational generalizations, research into that, but you also need a way of connecting these different observation generalizations into a single structure. That's where the theory comes in. Now, as far as the complications of the classification of habitats that you're pointing out, I think by classification, you mean something like a tree structure where each branch, branches off again and again, but no two branches converge. I think that idea has to be abandoned. What you have is a multi-dimensional classification where there are different parameters of classification, and they interact with one another. For example, one parameter of classification is temperature. And temperature applies to the classification that I earlier posed: temperature of water, temperature of air, temperature underground, and so on and so on. And there is another parameter of classification, which is nutrients, classification of nutrients. And these again cross-cut. So there is a kind of multi-dimensional classification, not a single dimension of classification. When you develop a methodological strategy for multi-dimensional, multi-level classification system, then you can get a much better theory. So again, I am talking about a methodological strategy for theory construction, which also involves a methodological strategy for classification. Theoretical classification, I don't mean the kind of classification that was done, Aristotelian classification and so on.
So there's a question in the chat box for you that you might want to address.
Given my eyes are not very good.
Given that you accept predictions about the past as predictions, what are your thoughts on the following argument made by many evolutionary biologists? Finding anachronistic fossils would disprove evolution. The proverbial Precambrian rabbit, the what's its name, shale, What do you think of such a prediction? It clearly gives conditions under which our theory is rejected. So I actually don't think that it is.
I don't understand
Again,
I don't understand how a fossil will falsify any prediction. First of all, what is the prediction? Unless I know what the prediction is, I don't know what kind of evidence would show that the prediction is false. And it is not something like a fossil that would conflict with this. You have to state the observation generalization about the fossils. The mere existence of a fossil says nothing. So that, when that kind of argument is made, I as a theory constructor, I say, what? I don't know what you're talking about. So it doesn't make any sense for a theoretician.
So as far as I'm, again, not as a paleontologist, nor as a development, and not as an evolutionary biologist, but simply as a biologist familiar with all the hot air that has been swirling around the Burgess Shale, which is where these Precambrian body form diversities were found, the body symmetry diversities, and so on and so forth. And the argument that all of those arose in a matter of 10, 20, 30, 40 million years. And that's simply, as far as I'm concerned, if at all it rejects anything, it might reject an evolutionary theory of strict gradualism.
Yeah.
But that's just a nuance.
Yeah.
It doesn't actually reject the heritable variation and natural selection functioning on heritable variation, leading to the emergence of surviving patterns as the theory of evolution. The precise mechanisms, as I said at the beginning, we enrich them as we go along. Yeah. So is the entire history of the Earth an unbroken chain of gradual, temporally gradual evolution? The Burgess Shale would then be taken as an argument to say, probably not. But beyond that, I don't see how that, in any empirical sense, rejects any argument at all. Although I'm aware that the kind of creationist arguers that Mo dissociated himself from at the beginning do use it for these purposes, but I don't see how that.
They don't understand predictions. They don't understand theory. So let's kind of ignore them. But I want to ask you about one of the words that you have been using consistently is heritable evolution, which kind of suggests that the only explanation for the diversity is in fact ancestry, as opposed to, for example, how would you explain homologies which are not from ancestry, but convergent evolution? Let me take a concrete case. The appearance of claws and claw-like things in plants which are thorns, and they appear in so many different organisms. And the examples of that kind are quite common. I don't have to, if you look at convergent evolution as one of the things that we need to explain, not simply evolution through ancestry, but evolution through some other mechanisms. If we have a theory of convergent evolution, I think the picture would look very, very different. Because then we'll have to, as a linguist, I would say some of the homologies of languages come from ancestry, but there are also others which come from universal constraints, and some of them come from borrowing. So there are three mechanisms for evolutionary processes: ancestry, universals, borrowing. And it seems that biologists have been focusing single-mindedly on ancestry type of explanation, but there are other explanations as well, not from ancestry, but from other kinds of things. And convergent evolution is one of them.
So as far as biologists are concerned, if it ain't heritable, it don't survive.
That may be, but that doesn't give you the ancestry, the kind of evolutionary explanation. Evolution based on ancestry is different from...
But But this is why I'm repeatedly pointing out that the empirical position is these are explanatory models where we are trying to put mechanisms together. And the bottom line is that if it is not stably heritable, it doesn't play a role.
Yeah.
Even the great what I consider to be true epigenetic rather than Waddingtonian epigenetic, which for me is just morphogenesis. The true epigenesis is epigenetic inheritance. The agouti mouse is an excellent example of epigenetic inheritance across generations of organism, not simply from one cell to another in my body, but from one, in this case, mammal generation to another mammalian generation, inherited epigenetically rather than genetically. It doesn't survive. Epigenetic inheritance is not multi-generational. And therefore, while it provides an additional and deeply interesting enabling loop, the fact still remains that if a variation is not transmissible across organismal generations, it plays no evolutionary role.
So that's one of the constraints.
And that's the argument of heritability.
Yeah.
This isn't about saying that patterns don't exist. Of course they do. After all, empirical biologists describe the patterns. It is about saying that patterns appear to emerge again and again, depending on how you define the pattern. So a thorn and a claw are not the same thing in some perspectives and are the same thing in other perspectives. So there are issues here. Horns, for example, in mammals can be completely morphogenetically different. So to call them the same thing is quite frequently a mechanistic error, a morphological error. But that said, biologists, empirical biologists, tend to keep pointing out that all of this is based on heritable elements. Because if it's not based on heritable elements, then it by and large doesn't exist.
Okay. So the plea that I'm making is statements of the kind that you made about heritability should be explicitly articulated so that you can take different propositions of that kind, put them together into a theory and deduce the predictions. One proposition by itself is an empirical statement that you can test, but then what happens when you combine that with other things? It is only when these things are put together into a configuration that you can make predictions. So this is where the observational generalizations, for example, if you state a single correlation, that's fine, you cannot make any large-scale predictions. But if you put together many correlations, put them together into a theory, a correlational theory, then it predicts things that were not originally present, new things. Those are the things which are testable. So the plea that I'm making is to take these individual generalizations into a theory, deduce the predictions, test them. That's a different methodological strategy. That's what I've been arguing for.
I take that injunction with all the humility that an empiricist can summon up. However, let me go back to a point that Garvat Bansal made. And let me make that again about COVID-19 and SARS-CoV-2. Here is the salutary acknowledgement.
Would you want to read out the comment by Darwin? Like, would you want to read out the comment by Darwin?
Well, I already made reference to the comment about the short-lived nature of predictions. That's why I didn't read it out. So he pointed out that truly going forward, predictions into the future evolution is capable of, seems to be capable of making really very short-term predictions and not long-term predictions, kind of like the weather. Yeah. So I think that's a good point. Yeah. But that said, let me point out the salutary acknowledgement, and let me point it out in the context of COVID-19 from my own field as an immunologist. We know about a huge pool of virus heritable element variations, because we have a massive number of individual virus genomes sequenced. We understand quite a bit about the immune response to the virus. Surely, people ask me, you will be able to predict what sort of variants are likely to come up in microevolution of SARS-CoV-2 virus as immune escape variants. And surely, because you can predict this in the microevolution of the virus as immune escape variants, we can now preemptively start building vaccines against these future immune escape variants. And the salutary public acknowledgement of the failure of my field of immunology in evolutionary terms is, no, we cannot.
If that statement is about Garvit's question, I think that is crucially tied up with what, well, physicists and people who study complexity theory, people, for example, in Santa Fe Institute, call sensitiveness to initial conditions and the chaos. And a classic example is the three-body problem that Poincaré discovered, that even though Newtonian theory of gravity is a deterministic theory, when you have, instead of two bodies, we have three bodies, two stars and a planet revolving around them, prediction in the long run becomes impossible, because that kind of interaction is extremely sensitive to initial conditions. So unless you know the initial conditions with infinite precision, which is in principle impossible, there are different pathways, and you cannot uniquely predict which will happen. All that you can predict is the range of possibilities. That's why I said constraints. You can say what is not possible, but you cannot predict uniquely this is what is going to happen. And you can also predict the probabilities. That's the best you can do when you have that kind of sensitiveness to initial conditions. And obviously, biological systems are complex adaptive systems. So you don't expect, the kinds of prediction that Galileo made about simple things like simple pendulum. Anything that is of a complex adaptive nature, you have precisely these things, three-body problems, because of the nature of the interaction. But that doesn't rule out the need for making predictions. But the question is, what kind of predictions can you make? In the long run, what kind of predictions can you make? And Santa Fe Institute has done a good job of isolating those things.
Okay, we've come to a logical point where we've lost audience, we've lost questions,
okay,
and we're almost out of time.
So I told you, the idea serves them right? So this was great.
Coordinators, is this a good time to say?
Yeah, yes, I think we could call this the end of the.
I should say thank you very much for a fantastic opportunity for a great conversation, Satyajit, and the organizers.
Thank you, Mo. Thank you, organizers.
Yeah.
Thank you, the audience, which asked really interesting questions.
Okay. So
thank you all for being part of this session. So I think this time.
All right.
Thank you all very much. Bye-bye.
Aditya, I think you can end the meeting now.